we have here a particular single solution to a differential equation that we're about to solve. It doesn't have any initial conditions attached to it, by the way. There are in fact infinitely many solutions, and this is just one of them. It's pretty cool. We will get a family of circles. In this case, our so-called arbitrary constant is taking on a particular value. It happens to be 6. And notice that with this circle we have a diameter of 6 units. So C is going to define our diameter, which is pretty cool. And this is just one value. C can take on any value. For example, right now it's negative 5 9/10. Right now it's 6/10, and so on and so forth. So we're going to get a family of circles. C can even take on the value of being 0, by the way, which is really weird, because then the question is, do we even have a circle then? Because the diameter is 0, thus the radius is 0. The so-called area of the circle must be 0. It must have a circumference of 0. Do we have a circle then? But besides that oddity, we will definitely get a family of circles. So let's look at the differential equation and solve it. And here is our differential equation. Prima facie, there's no way to separate our variables. However, notice the expression 2xy and the expression y squared minus x squared. This is a homogeneous equation of degree 2. And insofar as it really is a homogeneous equation, we can then do some appropriate substitutions, and then we can separate our variables. And as long as we can integrate, we'll be able to solve this equation. Let's stipulate that this expression here is the function m of xy. If we plug in m of t times x comma t times y, we get 2 times t times x times t times y, and that's just t squared multiplied by 2xy, but 2xy is just our original function, m of xy. And likewise, for this expression, we'll treat this as n of xy. If we plug in t times x comma t times y, we get t squared times y squared minus t squared times x squared. We can factor out that t squared, and that t squared is just multiplied by the quantity y squared minus x squared, and that's just our original function, n of xy. Thus, we really do have a homogeneous equation, and it is degree 2. This implies that we should do a substitution. We'll stipulate that y is equal to u times x, and then if we take the derivative of that, by the product rule, we would derive dy is equal to u dx plus x du. So let's make our substitution. And so we have 2x, and y is just u times x. We're essentially thinking about y in terms of the variables u and x. We can't say dy. We have to think about u and x, so we have u dx plus x du for dy. And then on the right-hand side, we have y squared, which is just u squared times x squared, then minus an x squared dx. And so we have 2u x squared, the quantity u dx plus x du. On the right-hand side, we can factor out that x squared, so we have x squared multiplied by the quantity u squared minus 1 dx. And like any good homogeneous equation, because we made our appropriate substitution, we have an x squared here and an x squared here. It's of degree 2. If we divide both the left-hand side and the right-hand side by x squared, we can simplify this. Or in other words, we can just multiply this entire equation by 1 over x squared. And so we have 2u times the quantity u dx plus x du. And on the right-hand side, we have the quantity u squared minus 1 dx. Let's expand this out or distribute. We get 2u squared dx plus 2ux du. And on the right-hand side, we have u squared dx minus dx. Notice we have a dx here, we have a dx here, we have a dx here. And it seems appropriate to subtract u squared dx from both sides of the equation. And this will just yield a positive u squared dx on the left-hand side. We can add a dx to both sides of the equation, and this just yields us a positive dx on the left-hand side. And then we can subtract a 2ux du from both sides of the equation, and so on the right-hand side we end up with minus 2ux du. Let's factor the left-hand side, so we have u squared plus 1 dx, and that just equals minus 2ux du. And by some division, we can separate our variables. So let's divide everything by x, and let's divide everything by the quantity u squared plus 1. And then we can simplify. On the left-hand side, we have dx over x, and on the right-hand side, we have minus 2u over u squared plus 1 du. Great. So our variables have been separated. All the x's are on the left-hand side, all the u's are on the right-hand side, and we can anti-differentiate. The left-hand side is just the natural logarithm of the absolute value of x. What about the right-hand side? Notice that in the denominator, we have this u squared plus 1. What's the derivative of that? That would just be 2u du, and that's on the numerator. So we're pretty much good to go here. So this is pretty straightforward. The right-hand side is just minus the natural logarithm of the absolute value of the quantity u squared plus 1, and then we'll throw in an arbitrary constant, c0. And remember that y is equal to u times x, and so u is equal to y divided by x. All right. I'm going to multiply this entire equation by minus 1. I think that'll make things a little bit easier. Maybe not by much, I don't know, but it seems the good thing to do here. So I'll say minus natural logarithm of the absolute value of x is equal to the natural logarithm of the absolute value of the quantity u squared, which is just y squared over x squared, plus 1 plus, I'll say, c. So technically our arbitrary constant changed, but just an arbitrary constant. And we'll simplify the left-hand side. We have this minus here. So that's just the natural logarithm of the absolute value of 1 over x. And the right-hand side is just the same for now. We can say e is raised to the following power, the natural logarithm of the absolute value of 1 over x. And likewise on the right-hand side, we have e raised to the following power. We have inverses of each other. So the left-hand side is just the absolute value of 1 over x. We could expand out, so to speak, this right-hand side as a product of two things raised that are where e is raised to a certain power. So e is raised to this power, and we have e raised to this power, to the arbitrary constant. And this is just some arbitrary constant. So now we have the absolute value of 1 over x is equal to c, our arbitrary constant, and that's multiplied by the absolute value of the quantity y squared over x squared plus 1. And now the question is, can we remove those absolute value signs? On the right-hand side, we have this y squared over x squared plus 1. That's guaranteed to be positive. Hence, we could remove those absolute value signs. On the left-hand side, we could remove them in the sense that the plus and minus, so to speak, will absorb into that arbitrary constant, right? Plus and minus c, yeah, we're good. So we have the following now. 1 over x is equal to c times the quantity y squared over x squared plus 1. But remember, I said the solution set is a family of circles. It doesn't look like a circle right now. So we're going to have to do some algebraic manipulations. Now remember that a circle on the Cartesian coordinate plane would be something like, we're thinking about the general form of it, right? So this would be the quantity x minus a squared plus the quantity y minus b squared is equal to r squared. So on the coordinate plane, the Cartesian coordinate plane, a comma b would be the center, right? And r would be the radius. So this is a general equation for a circle on the Cartesian coordinate plane. So essentially we're going to have to algebraically manipulate this and place it in this form of a circle. And by doing that we can say, hey, here is the radius, here is the center. Okay, so let's do that. There are different ways, I guess, to do that, but I'm going to multiply both sides of this equation by x, and I'm going to divide both sides of this equation by that arbitrary constant. If we have 1 over c, or in other words, c to the minus 1 power, that's still an arbitrary constant. So I'll just say we have c is equal to x times the quantity y squared over x squared plus 1. And I guess we'll just distribute that out. So we have y squared over x plus 1, pardon me, plus x. All right. Now what? So essentially, note that in a circle, we have some quantity, some x quantity, x minus something squared. And likewise, we have some y quantity squared. So that's what we want to end up with when we manipulate this algebraically. So right now, we just have c is equal to y squared over x plus x. And the only way I think this is going to work is if we multiply this entire expression, this entire equation by x. And so we have cx is equal to y squared plus x squared. So we're much closer. Then we can say we have z. Where did I get z from? 0 is equal to y squared plus x squared minus cx. All right, now we're much closer. Again, we want some quantity, x quantity squared. We don't have that right now. So we're going to have to complete the square. We're going to want to think about this. Okay, this is a quadratic formula. And as you know, if we have something like a x squared plus bx plus c is equal to 0, we also know that a plus b, that quantity squared, is a squared plus 2ab plus b squared. Okay, so if we say ax squared plus bx plus, I'll call the term d, is equal to minus c plus this d, we can solve that d, okay, because we're going to complete the square. So b, what would b equal? And this is the same thing as this 2ab, and this a is related to the square root of this thing, and this b here is related to this square root of this b squared thing. So this is just b is equal to the square root of a times the square root of d times 2. So we have b over 2 square root of a quantity squared is equal to d. So this is the key to completing the square. And so let's go on and do that. So we have 0 is equal to y squared plus x squared minus cx. So this minus c is the b term. So we have a minus c over a 2. A is just 1. This is squared. But we don't want to radically alter our equation, right? So we're going to have to also minus that that quantity. And so right here, we can simplify that. We can have a quantity squared. So we have 0 is equal to y squared plus the quantity x minus c over 2, and that quantity squared. And that would be a minus c squared over 4. Once again, note this quantity are equivalent. So we're good. And then, to finish this up, we can say we have c squared over 4 is equal to y squared plus the quantity x minus c over 2 squared. And now we do have our circle. Isn't that neat? So we have this. What's the center? So we would have c over 2 comma 0. What's the radius? It would just be c over 2, right? What's the diameter? It would have to be c, like we saw with the graph. So this is our family of circles. So pretty neat, and I hope you enjoyed that and had fun solving that particular problem.